Okay, good morning, everybody. I'm Elias Khalid from the University of Toronto, and with Adam Mashtouk from Columbia, we've had the pleasure to organize the masterclass for today on bridging the gap between machine learning and optimization. So we have a set of very exciting talks, 6 talks, 3 before lunch and 3 after lunch. The format is going to be 40 minutes for the speakers and 10 minutes for questions. So we ask that you defer your questions until the end, and then we'll take them in sequence. So our first speaker for the day is Professor T.S. Boons from KU Leuven. T.S. is an associate professor at the DTAI lab in Belgium. His research is at the intersection of machine learning and combinatorial optimization. And he's worked a lot on the integration of these techniques, so constraints used to solve scheduling, planning problems, and recently we have hybridization of machine learning systems with such solvers and tools. So we're very excited to have him here as our first speaker. Thank you.
Thank you very much for the nice introduction. I think there might still be some audio problems for the online visitors or not. Okay, so thank you very much for the invitation. I'm very excited to be here and to kick off this excellent program masterclass. So I'm very much looking forward to all the other talks as well. And so I will talk today about our work on perception and preference-based constraint solving, which is joint work with our members of my team, as well as with external collaborators. And so just to start off, it's Monday morning, so let's just start off very easily. I'm sure we all agree on what constraint solving is, but just for the record, so we're talking here when we talk about optimization, about solving combinatorial optimization problems, normally involving hard constraints and objective functions, for example, vehicle routing, scheduling. This is actually a hotel room assignment problem, packing problems, but also other types of combinatorial problems, such as Sudoku, graph coloring, and so forth. And so if we look at the current paradigm that we use, then this is often a model plus solve paradigm to solving these problems. And the model here is a specification of the constraints of the variables, an objective function, and then we can use a generic solver to solve any of these problems on the previous slides. But the question here is, where does this model actually come from? This model already comes from an optimization expert, you, for example, but in case of practical applications, this is in discussion with a domain expert, an expert that knows exactly what the domain is about, and vehicle routing, what the vehicles and the stops and other kind of side constraints of what matters to the company. And so if we look at the model and solve paradigm, but holistically from this point of view, then this is actually a quite rigid and a quite static process. And that is because modeling in itself is actually an incomplete information game. And so the optimization expert knows how to specify constraints, but doesn't fully know the domain in which it is operated, and so which constraints should be formulated in what way. Also, what we see is that in many cases, these domain experts start making ad hoc modifications to the model or to the solutions found. And furthermore, over time, the preferences might change. And so the kind of solutions that were desirable actually might not be so in a year or in 2 years' time. So these are all reasons that this model plus solve paradigm may not be fully satisfied. So I think this is one way to look at the increasing use of machine learning and combination with combinatorial optimization is actually to tackle some parts of this problem. And so I think we can group a lot of what is being done into 3 categories. The first category is about learning the constraints. So can we actually, instead of requiring to formally specify each of the constraints, can we learn some of them from data or from user interaction? The second category is about learning the objective function. And this could be preferences and how different kinds of sub-objectives are balanced off, or this could be costs or demands for external variables that has to be estimated. Now, finally, a big third group of work is about actually learning to solve, either to solve faster or even to omit the solver and to predict directly the solutions. And so if you look at this trend and the challenges of modeling plus solving, some people, or you might actually ask, maybe we can just omit all of the combinatorial optimization. Maybe we can just directly go from a specification, from the data that specifies the problem, and directly go towards predicting solutions in end-to-end way. And Many people in O actually find this a ridiculous question, but many people in AI are asking that question and are looking into techniques that way. And so I do think that we should ask that question and also come up with a good answer about in which situations this might be desirable and which situations it is not. And my current view on situations in which it's still meaningful to have a reasoning engine, to have a constraint solver there, is the following. The way that we look at it is that there's actually two types of knowledge. And the first type of knowledge is explicit knowledge. This is knowledge that is very easy to formalize and very easy to write down in terms of constraints. But there is a second category of knowledge, and that is implicit knowledge. In the social sciences, they call this tacit knowledge. And this is a kind of knowledge that you learn from experience. This is why one route planner in a transportation company can be much better than another route planner in a transportation company. And so if you look, for example, at vehicle routing, so the explicit knowledge is, for example, the number of vehicles that you have, the location of the stops. But then the implicit knowledge, if you go to a transportation company, the things that people actually also care about is things like, yeah, but can we estimate driving times? And service times, they also have a large variability. Can we actually estimate that and take that into account? Even the volumes at the stops can be subject to uncertainty. Then it becomes even more subtler and trickier. For example, driver experience. Some drivers are more experienced in certain neighborhoods or even with certain clients. And if you go even further, there's things like route intensity. The fact that some routes are actually much more taxing on the drivers than other routes. And so if you listen to the kind of way I start talking now, is that we're no longer talking in terms of mathematical abstractions like vehicles and stops, but we're actually talking about drivers. And most transportation companies have many more vehicles than that they have drivers. So it's about these vehicles are driven by people. And it's also not about servicing stops, but about servicing clients. So if we take this actually just one level further, then in constraint solving and the way that it's being used is actually much more than the mathematical abstractions that we use in our papers. So if we look, for example, at UN Sustainable Development Goals, then it has things like responsible consumption and production. So how can we ensure that our techniques lead to responsible consumption and production? I think that's a very valid question. And if we only take explicit knowledge into account, then we typically go looking only, for example, at economic costs, at factors that are easy to formalize. And that actually doesn't fully cover the picture. And I'm not convinced that it would lead us to reach these kinds of goals. And so maybe if we could make our techniques more suitable to include human values, societal effects and environmental impacts, all of these things that are actually implicit knowledge and are hard to formalize, if we could do that, I think we would be in a better shape. And so that's a large part of this motivation of how we want to look at problems as being partly having explicit knowledge easy to formalize and partly implicit knowledge, where we ask the question, can we learn this from data? And in this talk, I will look at two different settings. The first setting is that of preference learning. So can we learn hidden preferences, implicit preference in the vehicle routing domain by learning from historical solutions? And the second one is about perception. So it's a slightly different setting, but in this case, the implicit knowledge is how to interpret the images. So you're given images, and you need to interpret those before you can use your constraint solver. So this is a much more mathematical approach, but it's a very good framework to do research on this integration of learning and reasoning and how to get the best of both. So we'll actually start with the bottom one, with the perception one. So the work that I'll present in this part is actually based on this beautiful paper of which two authors are here in the audience. Dr. Weiler will present later today in the masterclass as well. And so this is the SATLab paper, ICML 19, where they ask the question, can we actually learn the constraints of a MaxSat problem from data in an end-to-end fashion? And so it was focused on learning the constraints. And in a way, what they were doing is they were testing the limits of learning reasoning problems. So how much can we learn the structure of a reasoning problem? But then when we were reading this paper, we were thinking, okay, from this perspective of explicit and implicit knowledge, the Sudoku constraints are actually easy to formalize, right? That's what we learn our students in first class. So if we know the constraints and we get the predictions, what can we do? And so the paper at some point talks about the limit that you have a predictor, it makes errors, and your reasoning system actually bound by those errors. But is it really? And so are we limited by the prediction accuracy of the neural network? So in this work, we wanted to test the limits of reasoning on predictions on a learned system. And so in general, this perception-based constraint solving has many more applications. For example, in document analysis, where you're working with scanned documents, in paper-based configurations like hybrid text form fill-ins, object-based reasoning, visual relationship recognition, and so forth. But we'll start with this pedagogical instantiation. So the visual Sudoku problem. In this visual Sudoku problem, you are given a set of images. For some of the tiles, you know that there is a small image, and that this image represents a number. And so you can use a standard, in this case, a convolutional neural network, to predict for each individual image what the probability is that it belongs to each of the classes 1 to 9. You take the argmax prediction and feed that into a constraint solver, which will solve a classical Sudoku problem. Now, if you have a moderately accurate classifier, so for MNIST, this is moderately accurate, but for other domains, this would be reasonable at about 95%. Then we see that in 85% of the times, the solver does not find a solution. So if you have about 20 images given, then the chances that one of those will be wrong, and it can be wrong in such a way that the solver doesn't even find a solution. All right. But what is really going on here? Why is this happening? And so if we look at it, what we're doing in this naive approach is that for each cell individually, we take the argmax over its multi-class predictions. And so we take the class with the highest likelihood, and we use that. But then we combine all of the predictions for all of the images. And so we actually treat this as a multi-output prediction problem. And we take all of the individual predictions at once. And this, what you get here, is the maximum likelihood interpretation, okay, over all of the images. And then we give this to a solver, and it says false, all right? So that means that the solver is telling us this interpretation is wrong, right? But that's just this interpretation. What about the next interpretation? Is that one also not leading to a solution? Or the one after that, or the one after that? And so instead of just settling for this, what we can actually do is we can treat this as a joint inference problem. And in a joint inference problem, we're not taking the argmax for each cell individually, but we're actually taking the argmax over each of the cells together, such that this interpretation, this labeling for each of the cells, satisfies all of the Sudoku constraints. So if the maximum likelihood prediction, the previous one, unconstrained one, satisfies all constraints, we're done. If it doesn't, it looks at the next one, the next one, the next one, next one, right? So this is actually the constraint maximum likelihood interpretation. And tying it back to machine learning, this actually treats the problem as a structured output prediction problem. And already in natural language processing, people have been doing that. Yes, question?
Are you assuming that all the images correspond to a feasible solution? Or
we do assume
you're learning?
No. We do assume that the input is a Sudoku.
Okay.
Yeah. So it is an important assumption. So it is a valid Sudoku. We just need to learn. We just need to interpret the images. For example, could be taken with a cell phone from a newspaper. All right. So this constraint maximum likelihood problem, can we actually use our constraint solving technology to do that? And the answer is yes. And using the standard log likelihood trick, we take the log of these probabilities, and our product becomes a sum. And so this minus log probability is actually a constant. And we're just talking about inference, about the forward pass. So the network gives us that. We take that. And then what you get is this linear objective function, where for each cell, and we have whether that cell equals a certain value, and 1 to 9 or not. And so this, you can give it to any existing constraint solver, and it will compute you the solution. So I think that's very nice. And we will see also that the results are pretty good. But we don't have to stop there. And so if we look more at this problem domain, that a Sudoku puzzle, a valid Sudoku puzzle, and only valid Sudoku puzzles, we actually know that by construction, it has to have a unique solution. But this is a property that is not easily formalized in a constraint solver. It's kind of second order constraints. But we have other techniques in combinatorial optimization to deal with that. We can, for example, add planes. And that means that if we find this joint maximum likelihood image that satisfies the Sudoku constraints, we can check if it has multiple solutions, and if so, forbid that interpretation. So we add a cut or no good, and we search for the next most likely. And so it's a deeper integration of the solving into the formulas. So if we look at the results, I showed you the first line before. So here, 85% of the time it didn't find a solution. By construction, now we will always find a solution. It might not be the right one, but we will find it. What's I think most interesting here is that by before, if you look at the image level, we had about 95% accuracy at the image level. If you actually project the changes that the reasoning does is it's able to correct up almost 5% of the mistakes that the network is doing. So by adding the reasoning on top, we're correcting errors of the neural network. I think that's a nice result. So now we are just using pre-trained neural networks here. And what we're doing is we're doing this joint inference over the raw probabilities. And you can actually stop and think, is this valid? Is this the right way to use this kind of neural networks? And actually, during learning, each image is considered independently. Each image is considered independently. And so that means that during training, we're just taking the softmax over the true class into account. And so it's actually well known in machine learning that convolutional neural networks can become overconfident and that they can lead to uncalibrated predictions. And if you're just looking for a single argmax prediction, that doesn't matter. But because we are interpreting these softmax values as probabilities, they can actually distort the joint inference problem. But no problem, no worries. So actually in machine learning, we have a lot of techniques to calibrate our predictions so that our predictions become more calibrated, so that they do satisfy that property. And we see that indeed, if we train our networks and add a calibration layer on top, then we get slightly better results. So that's something that you can take into account. But then you might wonder, especially in this masterclass, can we go even further? Can we just learn the neural network, ideally a calibrated neural network, directly by taking the output after solving into the loss function into account? So later today, you will see, I see many techniques that are able to do that. But here we have to consider the setting that we're in. So in this case, we assume that for each of the cells, we know during training what the true label for each of the cells is. And that means that what our constraint solver does is it corrects some of the errors, as I've shown you. But if you would use then the output after solving during training, then actually you would not get any loss or backpropagation over these errors that the network makes. So the errors that the network makes, but that the reasoning engine corrects, you would not backpropagate over. And so this would actually lead to weaker training. And these in preliminary experiments, we see that if you have the full cell labeling, then end-to-end learning in this case is not beneficial. But things change completely if you have weak supervision. So if you just know, if you're given images and you know that one of them is a valid Sudoku and another one is not, it's a much weaker signal than if you know the full labeling of each of the images. In that case, and that's also the case that the StatNet paper considers, in that case, this end-to-end learning does become the right approach. All right, so that was looking into perception-based constraint solving. So now let's have a look at learning preferences, but I should watch more time of it. How much time do I have?
You've only done 15, so you have 25.
25 minutes, okay, that's realistic. Maybe I should take a small pause. So I hope this was clear. These preferences, I think there was a year ago, I think, maybe a bit more. There's an Amazon last mile routing challenge. I think the way that they propose this problem also very much aligns with this idea of explicit knowledge and implicit knowledge. So for example, they wrote in this challenge that in real life operations, the quality of a route is not exclusively defined by its theoretical length, ratio, or cost. That's exactly this argument of explicit versus implicit knowledge. And so in this case, it's it's a weak supervision kind of setup. So you're given TSP solutions, and you know whether the drivers consider this, or the planners, a good solution, an average solution, or a bad solution. And the question is, can you actually learn what good solutions are, and can you make your solver produce these kinds of good solutions. But we actually started looking into similar problems already a number of years before that. So at CP19, we had this student paper on a very similar topic where we were working with a small Brussels-based company, transportation company. And so they use some optimization software, but then they actually made multiple changes to those solutions before giving it to the drivers. So the question that we asked is, okay, can we actually learn some of this implicit knowledge? Can we learn what some of their preferences are, so that what comes out of the root optimization software needs much less or even no modifications at all? So the goal here is to learn these preferences, to reduce the manual effort. But another advantage of such a technique would be that it can adapt to changes over time. So the transportation users, they can continue making these changes to the solutions, and each time we can retrain and we can actually adapt and learn their changing preferences. So that's really the goal here. But I must warn you that here we're in a question in the back, yes?
And you cannot learn or you cannot understand the constraints that they have, or cannot write them down.
No. So you should talk to them, right? So for example, so this is actually a sustainable transportation company. So then they say things like, yeah, so these vehicles are CNG powered. So if you want to reduce fuel consumption, it's better to do the biggest deliveries at the beginning. But it's also, we also like our drivers to arrive around at the same time, because then they can have a coffee together. And traffic is, yeah, so they care about it. And so traffic is especially bad in Brussels in that direction. So that should be taken account, but only if it doesn't make the routes go too large in number of kilometers. And then there's, so that they have lots of these things that they take into account. And sure, the classical approach is to sit together and have like session after session. And here we're asking, that's a valid approach, but can we actually learn some of these by just observing the kind of changes that they did, and thereby reduce the modeling effort, or in this case, because the modeling is already done, reduce the effort by the planners.
Yes, there could be some, let me say, random element in your preference.
Yes, absolutely.
That may not make sense to them.
Yeah. So there's no guarantee that you can perfectly learn their preferences. There's no such guarantee. Yeah, but it's still a valid question, right? How much, by just observing the changes that they do, how much can you actually learn and fix and like in the
There's also a question of what is the language of
Also, yes, what is the language of the preferences? What will be the language of the learning technique? And that will also determine what you can and you cannot learn. Yes. So I wanted to warn you that we are here in a small data setting. So in this case, we got 6 months of data. 6 months, okay, but that's actually just 26 weeks. And they drive on weekdays, so that's only 130 instances. Okay. 130 instances, that's really not a lot. And they also asked and to be able to continue to use their existing solver if possible. So before working in this domain, I actually worked a lot in data mining. And there in data mining, there's a lot of work for single vehicles. So for a single driver to predict where they are driving to or what kind of turns they are making. So in that literature, there's a lot of use of Markov models for a single vehicle. And so the question that we asked is, can we actually use similar techniques? So can we use this kind of Markov models, not just to learn preferences for a single driver, but actually to learn preferences across multiple vehicles? So what does that look like? Yeah, so when we learn these preferences, can we also optimize over them with existing constraint solvers? And so kind of learning that we looked at here, we started with simple first order Markov models. So what would a first order Markov model here be? That is, given that you are at a certain stop, so you only take the current stop that a vehicle is at into account. Given that it's at this stop, what is the probability that it will go to that stop or that stop or that stop? And so what we're doing here is, instead of using a distance matrix, we're actually considering transition probabilities, the probability of transitioning from this stop to the other stops. And if we can learn these kind of probabilities, then we can actually get a first order Markov approximation of the joint probability that a routing is the preferred routing. So this joint probability, we can decompose it into the probability that we start at the depot. We always start at the depot, and that we go from the depot to the first stop, first to the second stop. Right? So if we have these probabilities, then the goal is really to find this maximum likelihood solution. And I think you're already hearing the bells from the first part of my talk. And so we want to maximize the probability. It's actually a product of probabilities. So we then do the log likelihood trick, and we get a nice linear formulation. And actually, if you look at it more closely, what we're doing is we're replacing the distance matrix with the distance between each of the stops by the minus log probability of our preference model of transitioning from one stop to the next. So by doing this, any existing solver can be reused, including all of the hard constraints that have been set up by interaction with the planners. Okay, so what about the learning? Well, and it's a fairly standard Markov model, so you can use a counting-based approach. You create an adjacency matrix for each of your historical solutions, and then you count how often you transition from one stop to another stop. And this assumes that the transportation company often visits the same kind of stops, and that is the case. It was about 60% of the time. So not always, but in many cases they did. So you have all of these adjacency matrices. Now, what is important is you can just count all of them up, but it could be good to actually do this counting in a weighted fashion. And so if you know the stops that you're using today, maybe you should take the historic instances that consider like almost similar stops more, and that they should influence the probability more than others. Or maybe the more recent manually changed solutions should be more important than the older ones. And indeed, in our results, so the blue line here on top, that's the one where we just do uniform counting. So there's no weighting. We just take all of the historic instances as being equally important. But what we saw in this company data, and initially they all were very similar, is that at some point they had a change in a client portfolio. So quite a number of clients left, and they started hiring new clients. And so the kind of knowledge that they had about these new clients and about how to drive between them also changed. Now, what we see in this setting, so there's a concept drift, as we call it in machine learning at this point. So what we see is that if we actually do exponential smoothing over time, meaning that the previous instance contributes most, and the second one a lot less and a lot less, and so this exponentially decays. Well, in that case, this technique is able to handle this concept drift much better. So taking these weights or looking at exponential smoothing here makes a lot of sense. All right. So this was a first order Markov model, and the first order Markov model, let's admit from a probabilistic point of view, it's a very crude approximation. So what about a second order Markov model? That's a model that doesn't just take our current stop into account, but also the previous stop. And so this will be a slightly more fine-grained probabilistic interpretation. So what happens if we would use that? Of course, we can again use this counting approach with some smoothing. And then what we see is that if we look at the root level, so at the level of the accuracy of the roots, there is indeed an improvement in when we use second order models, but at the arc level, it's about the same. But most importantly, the solving is much slower. And so we here had to use a quadratic objective on a MIP formulation of a vehicle routing problem. So it was about 2,000 times slower. So much slower that it's actually prohibitive. So I think if you want to go to higher order models, you can, and maybe instead of using solvers, we should think more in terms of decoders. But if we do that, we're actually talking about learning a policy, reinforcement learning, and so forth. So I think a higher order, yes, but it actually leads you into a different kind of research approach, one that does not involve solvers per se. So we continue with the first order weight, so the learning the transition probabilities, but we still want to do the learning more accurately. And we can only take the current stop that we're in into account, but we can take more contextual information, or ideally would like to take more contextual information into account. For example, what day of the week it is, or some encoding of what the number of stops are that we are considering today. And so if we could use a neural network instead of this simple Markov counting model, then we could take these contexts into account. But there's quite a lot of challenges that are brought up to this. So first of all, we need to predict n times n outputs. That's quite a bit. And how do you represent the inputs? So you can encode a variable amount of stops, surely, but do you also encode the full distance matrix? And do you have all of the distances put in n times n and then calculations? So your network can blow up pretty quickly, and especially in the small data regime, that can be problematic. And then there's also the question of optimization. So let's look at one of the choices that we made here, and that worked well. We tried many things actually, so I'm only showing you one that worked well. The first key idea in this small data setting is to heavily make use of parameter sharing. So instead of learning one network that predicts the entire transition probability matrix, we're going to use one shared network that, given a source stop, predicts the probability to each of the destination stops. And this network is shared for each of the source stops. And so each one, so you always do just n predictions, you share it. And so that in that way, you have a lot of less parameters to learn. Now, if we present the earlier work that we did to an operations research audience, then they actually ask these very refreshing questions, such as, if you're learning the preferences the way that you do, aren't you doing imitation learning? That's how we call it in machine learning as well. We are indeed doing imitation learning, but if you're doing imitation learning, you're just copying what the planners are doing. And this is not an intelligent solution per se. It can actually enforce some of the potentially bad behavior of the current planners. I think this is a very valid criticism. You can ask the same about DALI, about Lambda, about GPT-3. Isn't it just copying instead of being intelligent? In operations research, we typically use constraint solvers because they can consider larger number of candidate solutions and because they can take the conflicts between the different components there into account. Okay, so if you talk to the planners, then the kind of argument that they say is that, yeah, this one might be shorter, but this one is only 2 kilometers longer, and I prefer it for that reason. So what they actually implicitly do is they have some kind of preference model, and they trade off their preferences with the impact it has on the distances. So ideally, the best kind of combination of both would be that you take the distance matrix into account, and you also take some kind of learned preference matrix account, weighted off with some appropriate beta. So if you want to think about using machine learning in this setting, then the simplest possible architecture that we could think of is, well, why don't we just try to learn the betas? We have the distances, we can use our exponentially smoothed Markov counting probabilities as a preference model. And then maybe if we learn an appropriate beta that does this kind of trade-off, then we would be already on our way. So it's just one parameter shared across all of the arcs in this case, but you can look at it as a simple linear layer, for example, 2 parameters in this case, and you already have a valid model. So that's a very extreme way of doing parameter sharing, but it's just a starting point. So you have your distances or exponentially smoothed Markov probabilities. Then you can add an embedding layer based on the weekdays, another embedding layer that gives information on the stops. And you can even try to learn what our Markov probabilities did. You can even try to learn this with a sequential model as some kind of LSTM over the historic solutions and have this. All right, so one question remains, namely what loss function can we use here? And in this setting, in this paper at CP last year, we just use the classification loss as a proxy for the R difference. So we don't call the solver, we just look at the probabilities given by the arcs that are part of the true solution. And we have a cross entropy loss over that. So what you see is that our Markov counting approach in terms of arc difference and root difference was okay-ish. But then if we do this neural network, actually, curiously, if we try to have this LSTM to learn some of these relationships, it doesn't work as well. And we think this is because of the small data regime. So if we leave that one out, we actually get better results at the arc and root difference level. And compared to the purely distance-based, that one is way off compared to what the planners want. Okay, so here, and so that's what we did. And then you might wonder, okay, this loss function is quite primitive. It doesn't take the solving into account. So how could we actually take the solving into account? Well, as I said before, we are treating, both in this case and the previous case, we're actually treating it as a structured output prediction problem. One of the most basic algorithms in structured output prediction is the structured perceptron by Collins, 2002. And it looks like this. And so on line 4, you call the solver. On line 5, you check if the solution is the same as the true solution, as the one that the planners manually changed. And if not, you do an update based on the solution difference. And so here you directly manipulate the W's. So it's not a neural network approach, but there are well-known connections between structured prediction and actually pairwise learning to rank. So the way that's the top of the slide. So the way to think about these pairwise learning loss functions is that your objective function, or actually you have the set of feasible solutions, and of all of those feasible solutions, one solution is the right one. Okay. And then if you look at the joint probability, so your transition probability model induces this joint likelihood, and you can use that to rank all of the feasible solutions. And the true one might be the first one, or it might not be. And in this case, this would be the top solution or resolution that the solver outputs, and we know that it's different from the one that the user prefers. So you can actually use this kind of pairwise ranking loss on the model. And actually, this pairwise learning to rank, and we made some further connections between learning to rank and decision-focused learning. So you can think of this as inducing, so the predictions induce a probability distribution over the feasible solutions. And in decision-focused learning, you can also think that the true cost induces a probability distribution. You can actually learn cross-entropy or Kuhlmann-Leibniz over these probability distributions. So I just want to highlight that although we didn't use it in that work, we are looking into this kind of connection. So we'll present this next month at ICMA 2020. One of the reasons that we're not using it for the case I just presented is that a key bottleneck in these approaches is that we need to repeatedly call the solver. And so in this case, we would make the predictions, so we get our transition probabilities, then we call the solver. It's a recoding, not a DSP, but yeah, we use that answer in some appropriate decision-focused loss, and then we backpropagate over it. And so one thing is that we want to look at how to actually speed this up. And so in many cases, the solving is actually an approximate solving if you do decision-focused learning. And so one of the observations that we found is that you can actually also store each of the solutions that you computed and use that as an approximation function. And so you can use these cached solutions as an approximate solve call and thereby avoid calling the solver and speeding up the learning blocks. So this works pretty well in a standard decision-focused learning setting, but in this preference learning setting, it doesn't. And that's because this caching approach is only valid if the constraint set is the same for all of your instances. And so that means that, for example, in the knapsack problem, the constraints, or in the scheduling problem, the constraints are always the same. But in this preference learning problem, each day we consider different stops that need to be visited. And so then we cannot use this caching. And that's one of the reasons that for now we haven't looked at that yet here. So to summarize, we looked at learning these tacit knowledge, these preferences. We can actually use existing solvers, and multiple learning schemes are possible, and many more remain to be explored. All right, so in my few minutes, so just an overview so far. So explicit implicit, treating it as a joint inference problem. And you can look at how to integrate learning into solving, but actually looking how to integrate predictions into solving is already a rich research domain, I think. And then we've seen that revisiting both sides, for example, the calibrations or the cutting planes, is actually a good approach. So to close off, if this is the standard model plus solve approach, then I believe that we should look at techniques where we can learn these implicit preferences or even learn cost and so forth from the environment by observing how these solvers are used. And then ideally, we actually want to go further. And we also want to give the possibility to the user to ask questions to the solver and ask, why did you make this decision? Why not this decision? What kind of predictions have you used here? Where is the uncertainty and so forth? And even more ideally, and this is like the grand vision, is that we would allow some kind of stateful interaction across the solving and the learning between the solver and the user. And this is actually the ambitious goals of a 5-year ERC project that I have. That's where we want to work towards co-creation of constraint optimization solutions. And I'm actually actively hiring postdocs. So if you're looking for a postdoc position in Europe, feel free to contact me. And with that, I hope you enjoyed it. And I'm very much welcome the discussion. Thank you.
There are microphones. There's mics there. There's mics.
All right. Yeah, it's okay. Okay, so we have about 10 minutes for questions. And maybe we'd like to give priorities to students, and this is a master class. So please raise your hand if you have a question. Yes.
So in the second part of the talk, it sounded, so I think the question of whether the optimization algorithm should do better than the human planner is really interesting. And it seems like part of the problem is that the humans don't have like very well specified preferences in some sense, right? There's like lots of different things they're thinking about in a way that's kind of hard to formalize.
Correct.
So I'm curious if when you have the setup where you have those contextual features and all of that, if you can set that up so that you can get an interpretable sort of readout of what people's real preferences actually are, right? Like when you, and then when you know the constraint structure that they have to work under, right? If that helps you basically back out like a concise description of what they actually want.
Yes, I'll shortly repeat it for the audience remotely. So it's about so like learning the preferences and whether you could have a symbolic representation of the preferences that are learned so that people can interpret the kind of trade-offs that you learned. That's the question, right? Do you agree?
Yeah, either symbolic or just,
Well, yeah,
like an interpretable, like
yeah, interpretable in some way
or something. Yeah.
Yes. So I think there is. So if you look at this simple abstraction, then you can actually show the beta parameter that is learned, and you can show, okay, we're actually learning like an 80% of the impact is from the distances and 20% is from the preferences, right? But this is only moderately satisfying because this is still a black box. And so I think here we're actually, I think the more my current view is that the more we want it to be interpretable, the more restricted we are in terms of the learning and the feature representation that we can use. If we use an embedding, if we use these kinds of embeddings, so sure we can expose the different kind of balancing. We can say that it's multi-output, a multi-objective kind of preference function over these network input, but these are on their own also neural networks. And I think up to this point you could explain up to that. Yeah, I'd be happy to learn more. So in the Amazon Last Mile Routing Challenge, a lot of our people use a more manual approach. So they actually identified features or like problem representations that are well, and then they have this multi-objective function and they can interpret it. So once you know the features, you can use machine learning to learn how to balance them off, even with these techniques. But coming up with the features, you either have to do it as a domain expert or you lose sight of what's going on, I think. Yeah, but it would be great if there would be a middle ground.
Okay, other questions? Yes.
Just a question from the Zoom people. So thanks for the exciting talk. I'm not sure I have understood how the underlying web solver uses the transition matrix. Transition matrix is output by the network to build an initial solution.
So actually what the network outputs is a transition probability matrix. So it's just between every pair of stops, the probability that if you're at this stop, you will go to that stop. And that can be used instead of the distance matrix between stops. So we take the log probability and you can use any VRP solver. So that's so it's not just the initial solution, right? We use an exact solver here, and instead of over distance matrix, it's over probability matrix. Log probability.
So more of a clarification. So your point on imitation learning is interesting. So does it suggest that like a 0% error would actually be bad? in this case? Like, because I'm literally just matching. Like, this is like
Yeah,
my
so,
question.
yeah. So when we talk to operations research people, then they consider that yes. Yeah. So they often assume that planners might have habits, and that is actually the case. So why do they prefer one solution, or why don't they actually prefer the shorter distance solution, right? And some of it could be because of preferences, because of, for example, that the drivers stop at the same time, or that you prefer that some stops are visited before others, because mathematically, if you just look at distances, then you can do a tour in any direction and it's the same. But in practice, we know, no, every transportation planner will tell you one of the directions is much preferred to the other, but that's not captured in the distances.
And when you just solved the problem with classic distances, I saw the table, it wasn't able to interpret it. What was the error on this?
Yeah.
And how did you measure error?
So if you look purely at distance, then the distance-based VRP gives you shorter distance routes. Using the preferences in this way, that's the number of average kilometers. So it's a bit longer, the tours. And how we evaluate, that's a very good question. So we look both at arc difference, so looking at how many of the arcs of the solution match the arcs of the true solution, or at a route difference, where we do like a pairwise matching of which routes are the same, and then how at the route level, how much overlap there is between the stops visited in those routes.
So were they surprised by this distance gap? I mean, they do care about
by this
gaps,
one,
right?
by this one they weren't surprised.
but the fact that there's significant difference.
No. Because they know that if they just optimize based on distance, that they would never drive it. So.
I guess this is a hypothetical question that combines sort of Adam's and Brian's question. So if you have a bunch of hypotheses about they have these preferences, right? They want people to go together, or they want the breaks of drivers to be spaced out. Could you incorporate those as constraints and then maybe trade off, learn how much they value specific preferences? And in that case, that would be, I guess, interpretable, but also
yes,
not the same thing as the planners.
Yes. So what you would do? So then you would actually formulate them as soft constraints. You put them in your objective, and then you could actually treat your objective function as being a weighted sum of sub-objectives. And these sub-objectives could directly be the features of your neural network. And then indeed you can learn how it balances off these different sub-objectives. Yes. Yeah.
At least for the VRP problem, it's not clear to me what you learn, because what you're doing is to change the objective function. Which in another way is saying that you change the exam question. Right? You change the exam question, you get a different answer.
No.
Right, but what does this mean?
So
if we allow students to do this, right? The result would be chaos actually for exams.
Yes, I really like this question. You're assuming that the model is correct. That's your assumption. You're saying, but if you're not using distances, then you're actually changing the model. And I'm telling
the
you,
distance is only part of the model.
Yeah, but I'm telling you that the domain expert never agreed with the model in the first place.
Right.
So through the optimization expert, this is just an approximation, an incomplete information representation from what kind of solutions they're looking for. And this modeling that is the real challenge.
Also, just a follow-up is that I think in the Amazon challenge, what Amazon wanted was to produce, get results which were learning based. But actually, the top solver was just classical.
That's the solver.
Right, and they just exploited the Amazon rules, and that was my interpretation. I could be wrong.
I think we have one of the winners in the Zoom.
So they did use a heuristic solver, which is the right approach, but then instead of using purely the distances, they added these learned objectives based on the zone on the zone information for each of the stops. And so it was a manual learning approach. I agree there was no machine learning. It was a manual learning approach, but it was still learning. And I think it's a valid question. Can we actually learn what they manually crafted? Can we learn it automatically? Yeah, in the back.
First, thank you so much for your talk. I was wondering, can you touch on perhaps the relationship between using machine learning to learn things, whereas inverse output?
Yes.
Can you use that?
Yeah, that's a lovely question. So the question was the relation between using machine learning and using inverse optimization. So is there a good slide I have for that? So in inverse optimization, you want to learn the weights of your objective function directly, right? And you assume that these weights are stationary, meaning that for all of your instances, exactly the same weights should be used. And what are the best possible weights such that for each of your instances, you get a good solution. And our Markov counting approach is that, okay? So the learning is the weights, the model is the weights. But here, what we're doing is we're looking at contextual inputs. So we don't just want to learn the weights, we actually want to learn a model that predicts the weights based on contextual information. So on a Monday, it's going to predict different weights than on a Tuesday and on a Wednesday and a Thursday. And so machine learning models typically work from contextual information. So they're not about learning the weights, but learning to predict the weights. And I think that's the relationship. But I'm sure that there is hybridization between techniques from reverse optimization and this possible. Yeah. Yes, I'm just going to.
Yes, we have time for about 2 more minutes for about a couple questions.
Thanks for a great talk. I know you briefly mentioned calibrated probabilities. I want to know if you can expand on how exactly that was helpful. Like argmax is the same whether you do calibrated probabilities or not.
Yes.
So I'm curious where the calibration actually helps.
Yes. So the okay. Which slide shall I use? So if you treat the argmaxes separately, then you only take the argmax for each individual into account. But in our joint inference problem, in the one that is written here, it might be that the probability of the most likely interpretation of this image, let's say that you have 2 images next to each other and they both are predicted to be an 8. Okay, so they can be overconfident. They might both say that, okay, we have 99% probability to be an 8. But ideally what you want is that perhaps one of them says, I think it's an 8 with 51%, and I think it's a 3 with 49%. And so if there is true uncertainty about this interpretation, calibrated prediction would not overestimate, say, 8, 99%, but would actually be able to say 8, 51%, or 3, 49%. And so because we trade off not just the argmax probability, but all probabilities, having a calibrated classifier can be better here, can be more. Yeah.
Okay. In the interest of time, we're going to have to stop here for the coffee break, but you can follow the speaker into the coffee break and ask him questions. And we'll reconvene in 20 minutes, I think, for Brandon, Amos, and Priya. Don't stop before lunch. Thank you.